When doing regression, there are assumptions. An assumption is something we start out believing true, because we assume it, until we have evidence otherwise. So let's take a look at how we'll do this and how it applies to our regression model. So right now, as you know, we've had this regression equation that the mean of y given some x, and that's what the line is doing. The line itself is the mean of the points. So if you think about all those points right there, the line is going through the center. And what do we mean by that? Well, the line is the mean of the points, or it should be. So at all points of different x's, the line itself is the mean of the data. So you can see right here, I'm putting a red dot about where the line is at. The line is kind of the mean of y given any sort of x right there. What we have next in this equation is we would have the true intercept. Now, we don't know what the truth is. We'd have to have a census, which means all the data to know the true intercept, but it's kind of a quantity we believe exists if all the data was something we had. Next, we have right here the true slope times x, which is the rise over run. Make sure to have your interpretations correct for those, but this is just how we write the equation in the mathematical sense. Next, you see the important parts relating to the assumptions. Right here, we have that there is a disturbance from the model. Now, this disturbance right here is actually random. Had to throw that in. And the random disturbance has a pattern, though. The pattern is that it's normally distributed, and it has a mean of 0, and it has a standard deviation that is constant. Now, that last part's very important because that's your equal spread. If we didn't have one value for this standard deviation, then the points, if we had a model right here with a line, could start to do something like this, where they start to have more scatter. So this is where we'd have a violation of the third part right there, where the residuals do not have constant variation or constant spread. The 0 is actually the linear assumption right there, because at all points there is a mean of 0, which means the line is the average of the points. And the first part, normally distributed, would mean if you were to go around your data at any point and draw a normal curve, it should make a normal curve around the residuals throughout the model, and the overall residuals should have a normal pattern. So these are key assumptions we have right here about the residuals. One, that they're normally distributed. Two, that the line goes through the data, and thus the residuals would have a mean of 0. And 3, that the residuals have constant variance. You've probably heard this as the plot doesn't thicken, or we don't want things like heteroskedasticity. We want homoskedasticity, which would be same spread throughout the model. Very important to know what this notation means and how it applies to our model. So we run into some issues right here, and you can see it with the equation. So the big part to realize about this is if we have unequal spread, the typical miss is different. You might be wondering, what does the RMSE look like, which is the typical miss the model makes? Well, if you have a model that looks something like this right here, here's a good model. A typical miss, visually speaking, is usually about half the distance out on the points. Whatever this distance is in the plus or minus sense is a typical miss. Now, that's not the way it's calculated. It's calculated with mathematics, and it's calculated the following way. RMSE stands for root mean squared error, also known as residual standard error. You can do the root of the mean of the squared errors, but check this out. When you think about it, root and square cancel, and you're left with mean error. So it's basically a typical miss because it's a mean error. Now, why don't we just take the mean error? Well, the mean error would be 0. And how does this relate to our checking of assumptions? Well, the slope is going to be calculated via this formula. The standard error of the slope, rather, will be calculated via this formula, which is our uncertainty in the quantity of the slope. So in this instance, down below, we'd actually have a good calculation of the uncertainty or standard error in the slope. The problem is if we have a non-constant RMSE, which would look like this, because now the typical miss gets bigger throughout the model. So we have a non-constant RMSE, we have plot thickening, heteroskedasticity. This value right here is not reliable because we have plot thickening. And since this value here is not reliable in this example, this value here is not reliable. And that means we do not have a valid understanding of the uncertainty in our slope. And from the uncertainty in our slope, the standard error, we get the p-value. Remember how to do the p-value? It's the estimated divided by the standard error. So if the standard error is not properly calculated, well, then that means our p-values aren't really reliable either, and our confidence intervals are also based on these, so the confidence intervals are not reliable. So it's very important that we have constant spread. Down below, you see at the bottom of the screen the constant spread. This is more important than ever that we have a constant spread to the model right here. And that's why we need it to calculate our model properly. So once again, right here, software is going to do all this for us, but it goes without saying that if we do not have constant spread, our model is not reliable. You want to see your points having a constant spread, like this right here, one of the key assumptions right there, that the points have about equal spread throughout the model. If they're not reliable, well, then everything starts to go away, like the standard errors are unreliable, which calculate the p-values, which calculate the confidence intervals. These are all calculated wrong, and their interpretations would be meaningless or unreliable. So we need to have the assumptions met to make sure our model is a reasonable reflection of reality. And that's one of the key words you're going to hear a lot right here, is that our model is a reasonable reflection of reality. We're not saying our model is a perfect reflection of reality, but reasonable means good enough. We want it to be a reasonable reflection of reality. So right here, to check the assumptions, we're going to start by looking at, is there a linear stream to the data? So is it linear enough? And that actually deals with this first part here with the 0, where the line would be going through the mean of the points right there, the center of them. The next thing we're going to look at is if it has constant variance, like we said. That deals with this part right here. And then last but not least, we're going to look at, are there any extreme outliers? And that would actually go against the normality assumption, which is at the start of it for the capital N, that they should be normally distributed. Now, there can be one or two weird ones because there's a few things, about 0.3% of the data is outside of 3 standard deviations according to the normal model. So it could happen, but it should be rare, and we should have larger data sets if it happens to any sort of data set. And here is where we get to the residual plot. So what is a residual plot? A residual plot is basically when you make the line flat and you look at the distance the points are away. And there's a lot of ways to calculate residual plots, but my favorite way is just to make the line flat and see the distance away. So the line itself, which is right here, would be when something has a 0 residual. Because anything with a 0 residual would be perfectly on the line. It didn't miss by any. Now, this is calculated a little bit differently, but you can kind of trace the points together. This point is the biggest residual, and it's over here. This point is the most negative residual, and it appears to be over about there, and then there's a few others in here, down there. You can kind of see where the points are at for this model as you look across, and the residual plot is going to show you how far away the points are. Now, when you look at a residual plot, the key thing is there should be nothing of interest. Nothing at all of interest in a residual plot. It should look completely random. Residual plots should look completely random, nothing of interesting, because they're the leftover parts that you haven't explained. So you want to explain everything and then have your residual plots just be randomness. That just looks like noise, things we can't explain, just random variation. These are other examples of good residual plots. They have a little bit of weirdness, but it's just because you don't have any predicted values in this range. So you can see that. Now, this one usually gets people down here at the end because they'd say, well, wait a minute, aren't we seeing some sort of thickening at the start? And the answer is it's due to more data at the start. If you have more data points, you see more scatter. If you have less data points, you see less scatter. Think about if you had a plot where you only had one observation over here and you had a whole bunch at the start. Well, that one observation is not a good understanding of the spread of the data. You really don't want something that extreme on the x-axis by itself, but you can't really understand the variation at that level of x because you only have one point. So usually you want your residual plots to look like this right here. You might get a little bit of weirdness, but nothing too bad is going on right here that would call our attentions and have us think that we did something that we shouldn't be assuming is true about our model. These, on the other hand, have major issues. If you notice right here, this is curvature. Remember, this is the line, and our points should be centering in on the line like this one does. You'll be able to tell the problem with this one, but that is where the line is at the center, and the line has a mean of 0. This one also centers in on the line, but it has outliers, and if you didn't catch the other problems, this one has plot thickening or heteroscedastic nature, where the plot is differing in spread, and then this one over here is a non-linear relationship, because the line is actually, here's the real means, and the line itself is not the actual mean. So that has a linear or nonlinear relationship when we have assumed that there's a linear relationship. So you can kind of see some of the three big issues right here. Once again, linearity, normality of residuals shown by outliers, and also unequal spread we call heteroscedastic. So in general, there can be little problems. Is this a little issue or is it a big issue? Now here's the thing, some of these things are a little subjective, but when we get to the test right here, the calculations of the test, they're going to be very objective on how we calculate them. So it can be a little bit of a problem or it can be a major problem. I like to grade them, and these all right here would get Fs, so we can just put some grades above these. F for you, F for you, F for you, but we're gonna have someone come along and turn it into an A. Don't do that. But these are Fs. These are about major problems right here, major issues with outliers, major issues with unequal spread, a major issue of curvature. These are not minor problems. We'll see some minor problems later when we look at some plots. Right here, we've got the over-interpreting right here. There might be a little bit of an issue here, but it's hard to say. Guard against over-interpreting, because is the majority of the data following a line? Yeah, it looks to majority follow it, and there might be it's hard to see, maybe a little issue here, but you really want to pick up on a big thing before saying there's an issue. This looks nothing like our previous residual plots, where if you look over here, the Fs are like, uh-oh, major issues. If I had to give this a grade on curvature, I'd give it a C+, and I'd say, you passed, you tried. So, all right. Yeah, I'm not happy about it, but yeah. So I usually think about giving it a grade, and where would it stand on the A to F range? Over here, we see some histogram of the residuals for normality. So if you take a look, there is a little bit of non-perfect nature, but the QQ plot is really what we want to look at. So I always say, don't look at the histogram, because histograms are subjective on how we create the bins. Look at the QQ plot for normality. How should a QQ plot for normality look? If it's normal, the points are going to mostly follow that line. What line are we talking about right here? This. That is the one-to-one match with the normal. If you kind of do, some people call it the fat pencil test, where you lay down a fat pencil, and if most of the points are on there, the vast majority, it's pretty good. And we have a little bit of departure down there at the bottom, but truthfully, that's not too bad. It's within the meh lines. I call these little dashes because it's kind of telling you these are the forgiveness lines to be like, yeah, it's pretty good right there. So overall, nothing too bad right here. Looks pretty good. I'd say pretty good. Everything's got little issues. You know what? We'll give this one right here a B+. Pretty good job right there. So going forward, here we see some more major issues. You can really see it over here. If someone told me this didn't have issues, I'd be like, this is the F. That is the F. Now this one is a borderline good. It's like, okay, you're doing all right. You got a C. You tried. Good work right there. So this one we're pretty okay with. It has a low extreme outlier. It has a little bit of oddness at the top, but the majority of it is good. But there's a little bit of weirdness down here at the bottom, and there's a little more weirdness up here at the top. But this one is the super mad Dracula angry face right here. We're not happy about this at all. That's, that is so far away from the line, and it even has problems down here. This is right skewed residuals, and we're not happy about this, and that definitely does not pass the QQ plot. You can also see the curvature in this model right here. When you look at this model right here, look at the data itself, and you can see the line right here, and the points start out above, and then as the points go around, you will notice that the points start out above, below, and over here. We got right skew nature to the residuals. Little bit of an issue here. This would get a C+. This would get a D-. Has some use. Maybe the line explains some of it, but I'm a little afraid with the curved nature of the relationship, using a linear model probably isn't the best idea right here. So how can outliers impact things? Outliers can impact a lot. When you think about the impact of outliers, they can drastically impact your slope right here, and they can impact Pearson correlation. So if you remember in 201, we say Pearson's correlation is changed in any way by outliers. You think of small points over here in a cluster, and then you put one point over here, and you've got really strong positive correlation. So the correlation itself is what calculates the slope. And if outliers impact the correlation, say it with me, if they impact correlation, they impact slope. What can outliers do to correlation? Anything. So what can outliers do to slope? anything. That's why we talk about no outliers. We do not like them because they're going to drastically alter the relationship. Here you see an example of outliers pulling the line down on the slope and also creating a strong relationship when there is none. We talked about a cluster of dots that have no correlation, and then all of a sudden you have one point making a strong relationship right there, and this is via the outlier demo in R. So how do we actually do these tests? Well, to do these tests, we're going to use p-values. So let's take a look at how to run them. Now, in a statistical test, we have to remember that we need a decent sample to do this. If we have a decent sample, we can create a good estimate that is reliable. But if you have too small of a sample, you might not be able to understand the result and come to a reliable conclusion. In these instances, we will often need to visually assess what is going on. So remember these steps. 1. Run your statistical tests. 2. Look at the p-values to see if they pass or fail. 3. If any of the tests fail, see if the sample size is at least 25. If the sample size is at least 25, then look at the plots associated with that test and give them a second chance to pass. Now, I know that's a lot to take in, but we're going to be doing those steps here in one moment, so get ready. So let's start out right here looking at what it means to pass one of these tests. When we pass a test, the p-value is going to be greater than 0.05. And I know this is reverse for you. You're probably thinking, wait a minute, I thought low p-value is good. All a low p-value means is that you reject the null hypothesis. So the null hypothesis oftentimes is linearity is good, equal spread is good, and also normality of residuals is good. That's not the technical way of saying it, but it's how we'd explain it in the business world, that we've assumed we have linearity, we've assumed we have equal spread, and we've assumed we have normality of residuals. So when we have a low p-value, that means you're rejecting that assumption and you're saying you don't believe it's true anymore. I reject that linearity is good. I reject that normality is good. I reject that equal spread is good. So in this instance, in this context, if we want to use our model, low p-values are very bad for us because it means we've rejected key assumptions that we don't want to reject. Now, once again, as we stated, when you only have a few points, you might not know what's really going on. So looking at it visually right there might not be the best idea. So we will rely on the test when we have fewer than 25 points. If you have 25 or more points, you get to give it a second shot. Think of it as like a second chance to redeem your model by viewing it visually. It's because these tests can be overly sensitive for large data sets. So you might have a little bit of weirdness, and then you say, you know what, I looked at the plots and it's okay. You're going to see examples here in a moment, but we'll do just that. So the test for linearity right here is going to try and see the linear relationship between the data and the predicted at all the values of x and the values of y, and see if we follow the linear pattern. It's going to calculate first the sum of squared errors of the saturated model and the regression model, calculate the p-value of the difference in the sums of squared error between the models, and then if the p-value is greater than or equal to 0.05, the saturated model predicts y no better than the regression model, implying that the linearity assumption is reliable. That's a lot. Here's the thing. The important thing to know, if the p-value is greater than 0.05, we pass. That is what you need to know. So we want to make sure we have high p-values when we are checking our regression. Here you see it right here, and we can run this and see right here what we get for a p-value. The p-value for this model we saw that looked kind of iffy, when we do the test, comes back as 0.23. So is that good or bad? It's very good. That means we did not reject that it's linear. We would continue to believe that it's linear, and we can keep our assumption about the model. Here's another model right here with a p-value that is basically 0, 0.00000017. And when you look at this right here, you can see it clearly does not have a linear relationship. And that means we reject that it's linear. We have evidence it's not linear. When we do the equal spread assumption right here, we'll use the Broch-Pagan test right there. And to do this, when there is equal spread, the typical size of the residual is going to stay pretty much constant throughout. When there is unequal spread, the typical size of the residual, about how far they are away, will differ throughout the model. Now, once again here, we want high p-values if you want to use the model. Remember, this is a reverse of thinking, so you usually think low p-value good, reject the null. But the null right here is that there is equal spread, equal vertical spread throughout the model. So if we reject the null, we're rejecting that there's equal spread, and we don't want to do that. You can see different ones right here. Take a look. Here's the model itself with the unequal spread. Here's the residuals right here. And yeesh, that's bad, that's bad. As in, the p-value is super low, so we would reject that there's equal vertical spread and have evidence of heteroscedasticity or unequal spread. Now remember, this makes a lot of the model unreliable, and we wouldn't want to use this model. Unfortunately, we're probably going to have to toss this model right here. Normality of residuals right here, this is done via the Shapiro-Wilk test. And the Shapiro-Wilk test is once again going to have an assumption that we have normality. So the normality is assuming the data, or the residuals, follow a normal pattern. So we got all the residuals together, we looked at every single one of them. They should follow pretty much a normal. And if the p-value is high, that means we retain our null, which means we still believe the data is normal. So we hope to have a high p-value on every single check assumption if we want to use our model, which is usually the case. And you can run all these tests right here by running check regression m right here, where m is your model. We've probably run m store into lm y tilde x comma data equals the name of your data. And this is how to create your model. And once you've created your model m, you can check the model with check regression. Let's go look at some of this output right here and see what we see. Now, interestingly, the first thing you want to look at when running check regression is going to be your p-values. Here's your p-values. So what do you think? The p-values are going to be linearity first, and with linearity first, we see high p-values. The next p-values we see right here are for equal spread. And once again, the equal spread p-value is also a high p-value, as is the normality of residuals right here. And so this means we actually pass all the assumptions. That's it, step one. Are your p-values higher than 0.05? Are they all higher? If so, you're good. Your assumptions are met. Now, something to notice right here is this p-value is here twice. This is because the x variable makes the model in simple linear regression when we have 1x. So it's actually a repeated test. When we get to multiple regression, the overall model will have a separate p-value to see the linearity of the overall model. But right now, those p-values will be duplicates, looking at the linearity of the x, which is the model, so it is redundant at this point. But this means we're good. This model is a reasonable reflection of reality. How about the next one? Well, you might already see some of the problems, but let's look at those p-values. Yeah, these p-values are not good. The p-values right here are all bad. Those are as bad as p-values get. As in, we reject that the linearity is a good idea for this model. We reject that equal spread is within this model. We reject that normality of residuals is something we see in this model. But there's a second chance. Remember, if you reject any of these assumptions, you can look at the plots as long as your sample size is at least 25. So do we have a sample size of at least 25? Yeah. Our sample size is 522. So let's go look at the plots. Time to do some grading. Normality of residuals, which is this one right here. And this one right here has equal spread and linearity. So for normality of residuals, I'm giving this a D-. It tried in this region. It tried there, but everywhere else it's really bad. Sorry, equal spread, that gets an F-. Linearity, you know what? The line, which is that right there, there's the line. I'm giving that a B+. You know what? 1 out of 3. Linearity is the line cutting through the middle. Remember, the average residual should be 0, so it looks like the line slices through that pretty well. So you're saying, is the line the center of this at all points? It kind of does look like that. Came back with a p-value of 0, but 1 out on the second chance. But I'm going to throw away this model because there's major problems right here. Regression is not appropriate. It failed 2 out of 3 pretty bad. The other one I was nice on. I mean, not too nice. It did all right, but not a good idea. Here we go with the third model right here. You can see the plots, but let's go look at the p-values first. Okay, so how many of these did we fail? We only failed 1, which means we only need to go and look at the normality of the residuals. So let's go look at the normality of the residuals. Over there. I'm going to give this a B, just a flat B for the normality of the residuals. There's two extreme outliers. You can see them over here. I mean, I'd be hesitant. I'd want to know what's going on. I'd look into the data. So I'd want to look into it. I want to see what's going on. Are those miscollected? What's going on? There's some extreme outlier there. There's one extreme, another one that's kind of bad, but overall not too crazy. It's got a shot. You know, it only failed one. Everything else looked good. So pretty good. Ooh, interesting data here. So let's go look at the p-values. Oh, all the p-values are very, 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 very what? All the p-values. They're very bad. Because remember, we do not want low p-values, which means we reject all the conditions or the assumptions. So going back here, you can notice, first off, let's look at the normality. This might be one of the worst. I'm going to give this a C+. We have here the equal spread. You know what? Equal spread. Equal spread, you're going to get a A-. I really don't have any much problems with that. I've seen better, but pretty good work. Pretty good work. Then we go over here to the line going through the center. I really don't see much. I think I kind of drew that a little bit weird down there on the bottom, having that spread out more like that. I think, oh, because of that outlier. Well then, yeah, well, we caught that outlier over here too. There's that outlier down there. So this little weird point down there. But the linearity, I'm going to give that give it an A- too. This is your report card right here, A-, C+. I'd say not too bad, not too bad right there. It's, you know, formula is probably still pretty accurate, especially since the equal spread weighs heavily on the formula and the calculations. But overall, we could probably go ahead and use regression right here. All the tests were failed. Tough call, but I'd say go ahead and use it. Well, we've seen a lot of problems with our regression, but how can we go ahead and fix these things? And the answer is with transformations. So transformations are going to allow us to fix regression in many, many ways. So really, anything is possible when it comes to transformations. You have the relationship between y and x right now, but you could do the log of y, the log of x. Any sort of transformation you want that manipulates and changes the variables, which then creates a relationship that might actually work better than the original variables. So you can see right here, we could take the square root, we could take the log, but the question becomes, how do we figure out what thing to do? Well, there's this little fish right here called an abalone, and they're a delicacy. So go ahead and read the Wikipedia if you like, and we're going to look at some relationships between the data and see how we could possibly fix it. This data is clearly not linear. Looking at this right here, you can see there's a strong, strong, strong bend to the data, very strong bend to the data. But what if we had a function to look at length and shell weight and see if there's any sort of transformation that we could find that would make the data work better? Well, there might be one. And so what we want to do right here with the code is take the variable, so we're taking the variable here, apply a transformation by raising it, square rooting it or something, store the variables into y and x, and then we can use LM or plot and show the relationship. Now, if you look at the data, it's much more linear, and the residuals, if we were to kind of think about them, are much better. There's more equal spread throughout the model. There might be some weirdness towards the end right there, and that's just a zoom in on the second graphic on the right. It's a zoom in of this portion right here in the data. You can see overall this looks way, way better. So as I mentioned, we are going to use the find transformation function right here. The find transformation function goes across a vector going from -3 to +3 by default, and it looks for any transformation within that range and how it impacts r squared. R squared being the percent of variation explained. So what we're trying to do is we're trying to find the best transformation that increases r squared the most. So all we need to do to run find transformations is load up reg class first, and then save our model into M, or whatever you want to call it, with y tilde x comma data equals, and then from there run find transformations. Just think about what the code is called, find transformations. Let's see what we get. Here we get a list of possible transformations. The best transformation is going to give us the following r squared. All of these other ones are within 0.02 or 2% of the r squared. So the truth is they're all kind of about the same. So if you had a preference right here, if you're like, I'd rather just use the -1 power because these fraction powers are a bit weird, you could use that. So everything here is kind of a candidate transformation, but the best is always at the top. And an important thing to notice here is the difference between ours and the best. If we had no transformation, then we would get an R-squared of 75.8. That's 75.8% of the variation in the y variable explained by the x, but now with transforming it, we get a percent explained in the y variable of 95.1%. One downside to transformations is you would lose a lot of interpretability, like what is a -2.25 power of the x mean? It's kind of harder to make a descriptive model from this. We get more of a predictive model from doing transformations. And you get the graphics. So when using fine transformation, you can see what your original data looked like without any transformations, the highest R-squared, the second highest R-squared, and the third. What do you notice about all of these R-squareds that are super duper close to each other? Well, they're all about the same. And now from here, when you run fine transformations, take a look at the powers it gives you and use your x and y variable name and store those into the new x and y that you want to transform. So you will then use the powers it gives you from fine transformation over here. We'll highlight that for you to see. So we'll use the powers over here and multiply our x and y by those. This will help us choose the proper transformation or the best transformations for us to use to have y better explained by x and also fix issues with linearity. So here you can see where we've done this. We've made an x transformed and a y transformed. We're making a model transform down there, and then we can plot this model and take a look at what's going on. You can get the log 10 transformation by doing log 10, and this is denoted in the output when you get a power of 0. So the power of 0 right here is going to be when we are doing the log 10 transformation. The log 10 transformation is denoted in the function with power 0. Here's the output right here with the x transformed variable and the amazing R-squared. And it's much harder to interpret this model because it is in transformed units. We oftentimes, as I said, look at this as a predictive model, and then we could untransform the model. So we can check the transform model here, just like we were checking regression, and you'll notice, how do these p-values look? The p-values look super bad because we failed all the tests. But remember, after we fail all the tests, what do? We check to see if we have at least 25 observations, and if we do, we can look at the plots. And the plots right here, other than, well, that's really bad. And we do have this. We've got outliers over here. So the equal spread is going to be a D. The linearity, we'll give an A plus to the linearity. That line was super awesome. And the normality of residuals is going to be a D minus also. I'm being nice with that D minus. So something we run into here is all models are wrong, some are useful. And when you think about this, this model has major issues with the equal spread, which is a bit of a problem, remember that, on a lot of the calculations. And also we have problems with the normality of residuals, but maybe it has some use because the R-squared of it's 95%. It's way better than the previous model too, because if you look at the first model we created, it had major problems. No way would a line be good for this. If you think it's not the best model, which it's not, statisticians disagree, we can at least all agree it's better than the previous model and way more useful. So we try to improve the model and get it to something we can work with here. 95% explained with some issues. We can work with that. We can probably use it a little bit. Untransforming your variables, lots of ways to do this. And we suggest using things like Wolfram alpha. There we go. And with that, you'll notice right here, we really focus on untransforming the y. This is because if we use it as a predictive model, we would just simply input the length of the abalone, which is the fish, and get the shell weight out of it if we're trying to get a shell weight as a variable we're interested in. So you do not want your y variable in transformed units. You want your y variable to be untransformed. So when you focus on doing this, you can focus on untransforming the y variable. And once again, Wolfram alpha is going to do a lot of the transformations for us. If you notice right there, solve right there, and you get the solve showing you how to get it right there. And here it is in an untransformed format for you. So we highly suggest using programs like this or other ways of solving it using mathematics. So go ahead and enter these prompts into Wolfram Alpha and solve the variables right there to make sure you have solved for y. Here's another example right here where y is raised to the negative 1/2 power. So the 1/2 power is a square root, and the negative flips it to the bottom side of the equation. You can see it right here. And resolving this out, solving for y, we get the following equation solved for. Another example on the screen here with the log 10 of y, and it does all the solving for you. And we get y in its final form right here, solved out right there with y solved out. And we just want to make sure it's a predictive model now. There is the primer right here on untransforming by hand, and there's a lot we can use this for. So if you want to untransform by hand, here's how to do some of the transformations, and I'll let you read through this and see the transformations doing the mathematics to solve each one. So feel free to pause the screen and have any of the transformations here used to untransform y. Outliers are a very important topic. Outliers can do anything to regression. So which of these points right here would be the greatest outlier? Well, an outlier is going to be something far away from the model. So that blue point right there is not really an outlier in the model sense, but it's more of an outlier in the XY sense. But let's focus on points that are more of an outlier in the model sense, which are going to be these right here. Something that does not follow the bivariate trend. So when we have an outlier, it's far away from the model, and it influences the model more than the other points would normally do. Notice how the line right here shifts drastically due to the influence of the outlier the line is pulled towards it. So we don't want these points overly influencing our model. Also, when we look at the value of r squared, remember r squared can be calculated by correlation squared. Well, if we had a strong correlation right here, an outlier could drastically impact that correlation, bringing it closer to 0. Same thing if we had a weak correlation and we have 1 point making a stronger correlation. So the effect on r squared, outliers can drastically impact r squared. But how do we deal with outliers? Dealing with an outlier depends on what the outlier comes from. If we have an outlier we know is an error, we can toss it out. But we have to know it's an error. What if someone told you they studied 10 days a week? Well, that's not possible. Now, what we'd love to do is go back to the original data and talk to that person and try to correct the error. But if we can't correct the error, we might just have to toss it out, especially if the data point is not reliable. So in the best case scenario, we correct outliers if they are an error, but not all outliers are errors. Just think about things that are unusual, that are far away from the model. We might have someone who scores higher than predicted. We might go to them and talk to them and be like, well, what's going on here? There might be a lurking variable that comes into play. And then we find out, oh, wow. And then we try to push more people towards the outlier to have people score higher. So outliers can be due to common cause things or special case things, but we want to have data that is real. So really the only time you toss out outliers is when you know they're an error. In other instances, you keep the outlier and you often try to explain them. So sometimes your model has too many outliers. And if we have that, we might try to see what's going on right here. Abandon the model, but don't abandon the data. So don't toss out the points. Try to make a model or try to find something that works with your data, because we're not in the business of tossing out data. We're in the business of explaining data. With that, great work. If you have any questions, feel free to ask. We're always here to help.